the previous tutorial, we have seen what are the effects of the switching frequency and the values of filter inductance on the output voltage. Here, as you can see it on the screen, the green color waveform is the output voltage and the orange color waveform is the voltage across the diode that has been filtered by the inductor. So we have seen the effect of changing inductance. So let us say I am reducing the inductance now. So I have reduced it from 900 micro to somewhat 400 micro. So it is evident that the peak to peak ripple voltage has been increased. So what we try to do in this tutorial is we try to compute the expressions for this trajectory what you are seeing on the screen. So we have started with a simple chopper circuit, and we have also seen that the output voltage is V0, which is varying something like this, isn't it? And the voltage across the diode is basically a pulsed waveform. So what we try to do is we try to solve the currents and try to find out the average output voltage that is appearing across the resistance. This is R and this is L, right? So it is interesting to note that this part of the circuit is the only nonlinear element, right? The other part, as highlighted in blue, is a very good linear time invariant system. So how do we go about and solve this system? It can be noted that when switch is turned on, the circuit would take the shape like this. Here the switch is turned on. This we can call as mode 1, and when the switch is turned off, this is the circuit. So in this mode 2, when it is turned off, this we call as on and this we call as off. So basically this is the mode in which the initial condition of the inductor current is getting decayed through a resistance. But in this mode, the system is having a forcing function Vg, whereas here it is 0 volts. So let us try to write down the general equations which govern these two modes. So we have this Vd, voltage across diode, is equal to L di by dt plus R. Assuming that we are starting from some initial current, call it as ILK, and we try to solve this particular equation for current. So IL of t for this particular interval in mode 1, we can directly write it as IL, ILK, the initial conditions which decay, this is the natural response of the system, minus RT by L plus the forced response of the system, Vg by R, the final current that it will eventually reach, into 1 minus e power minus RT by L. This equation is valid in the time interval 0 less than t less than d into ts. So what is duty ratio? We have already discussed that this is the switching time interval and this is the turn on time. So t on by Ts is what we refer by duty ratio. So let us call this. Oh, we have to substitute now that we are at the end of this interval, right? This equation is valid in this interval. Then the value of current that is at the end of this interval will become the initial condition for this mode 2. So let us try to find out what is its value. For that, I have to substitute T is equal to dTs in this expression. So in doing so, we can write that we can write it as, we can give some notation IL K dash. We have called this initial current as IL of 0 is equal to ILK. We are calling this particular initial condition as IL dash of K. So it could be, we are taking IL of 0, we can equivalently call it as IL of K, like it is the kth instant, then IL of K plus D into Ts is what we are calling here as, oh sorry, we are just introducing the notation of K so that it is more general. So here in this case, we are generalizing this particular initial condition as K plus D into Ts. Okay, this we have denoted with ILK, and this we are denoting it with ILK dash. So what is ILK dash? It is just, we need to substitute in the place of T, we will substitute TTS. So what it would be, IL K dash is equal to ILK into e power minus RDTS by L plus Vg by R into 1 minus e power minus RDTS by L. This would be our equation 1. So now with this initial condition, we will go into the mode 2. So in the mode 2, we have already seen that in the mode 2 there is no forcing function, there is no voltage that is driving the current, it is just freewheeling through the diode. So in mode 2, this initial condition becomes this initial condition will start to decay. So if we are talking about mode 2, this is the time interval that we are interested in, isn't it? I am just generalizing the things so that it is more placed in a better form and shape. Now L into dIL by dt plus I into R is equal to 0 is what we need to solve, and we already know that it is just the initial conditions decaying, right? ILK dash into with the time constant of e power minus RT by L. So if we just try to plug in what is IL dash and see, I'm just trying to plug in the equation number 1 into equation number 2. So that we will end up with ILK into e power minus RDTS by L plus Vg by R into 1 minus e power minus RDTS by L, the whole thing which is the initial condition into e power minus R 1 minus dTs by L, right? So when we rearrange this, that is equal to IL of k, just denoting it as k. What we are trying to do is we are trying to bring up a sampled data model kind of arrangement. Like we have a, we are looking at the points where this is IL of k and this is IL dash of k, and this would be my IL of k plus 1, because under steady state these two values should be equal. So this is what I am trying to call as IL of k and IL of k plus 1. There is an intermediate initial condition here. So that's why I am replacing ILK with IL of k. It could be the same or it could be different based on whether the system is in transient or it is in steady state. So let's just go into the math. We have here IL of k into e power minus r ts plus 1 by r e power minus r 1 minus d ts by L minus e power minus r ts by L into Vg. How did we get this? It's just the rearrangement of the above equation. Let's just multiply. It's so easy. Look, this multiplied with this, what will happen? E power, the powers in the e will add up. So d and 1 minus d cancels out, d cancels out, and we will end up in e power minus rts by L. Sorry, there should be L here. And then for this, the 1 into e power minus r into 1 minus d ts by L, and the same happens when we multiply, the powers will add up and it will result in e power minus rts by L. So if we see, just I'll rewrite this into e power minus rts by L plus 1 by r into e power minus r 1 minus d ts by L minus e power minus rts by L into Vg. So the reason why I rewrite it is because this is what we are calling as A, and this is IL of k, and this particular guy, he is B of d, which is a function of d, and this is Vg. So anything familiar from this? We are trying to keep this in a form that we call as x of k plus 1 is equal to a into x of k plus b into u of k. So we are trying to bring the equations into a discrete form, which we can be calling that as sample data. We are sampling at the instance k, k plus 1, and so on, right? So now we have such kind of arrangement here. So let's go further and try to establish the fact that x of k plus 1 is equal to x of k. That is, we are assuming that the circuit is in steady state. If you remember that the motivation towards deriving this equation is to obtain the output voltage under steady state. What is the output voltage? What is the output average voltage? That's we are interested in. So this is the criteria for steady state in discrete domain. What would be in continuous time? It is x dot is equal to 0, right? So now let's impose that. We already have the equations for x of k I mean, sorry, I got carried away with x. So here in our case it is IL of k is equal to IL of k plus 1. As I have mentioned that we have started with some initial condition, there is some other initial condition, intermediate initial condition. This is when we have turned on, and this is the moment when we have turned off, and again we are turning on. So we are reaching somewhere here. So we have an equation for this and we have an equation for this as well. So and we need to and we know that this equal to this if the circuit is under steady state, right? So I'll just rewrite IL of ILK is equal to ILK into e power minus RTS by L plus VG by R into e power, sorry, there should be dash here, into e power minus R into 1 minus t Ts by L minus e power minus RTS by L, right? Oh, 1 second, I think I have done a mistake here. This should be ILK. How? So what we are trying to derive here is, we know this equation and we know IL of k. So we are trying to find out IL of k plus 1. How do we find IL of k plus 1? IL of k plus 1 is nothing but, we have this equation, no? In this equation the time should be Ts. If we substitute Ts in this particular argument, we will get IL of k plus 1. So, and that would be equal to IL of k. This whole term represents IL of k plus 1. So, if we equate both of them, we can calculate IL of k. IL of k is equal to, just rearranging the terms from left to right and just isolating the IL of k, we'll get Vg by R into, sorry, let me write it in a different place. I hope this is not confusing. So IL of k is equal to Vg by R into e power minus R into 1 minus d Ts by L minus e power minus RTS by L divided by 1 minus e power minus R Ts by L, right? So this term we have taken to the left, we have taken IL of k as common and remaining all comes in the denominator. So this is what ILK is. Okay, so now let us see how to simplify this. Can we simplify it? In what circumstances we can simplify and in what circumstances we cannot. So basically we have these exponential terms, right? So this exponential term e power lambda s, let us say, where lambda is equal to minus R by L. Okay, so this can be expanded as a series. So 1 plus lambda into Ts plus lambda Ts square by 2 factorial and so on so forth. So we can either do a first order approximation or we can do a second order approximation and so on. So when can we do that? If lambda Ts is far the magnitude of lambda Ts is far less than 1, then the higher terms will not contribute much to the sum. So the most of the sum will be dominated by these first two terms. So in that case, what does lambda ts mean to us? It is minus r by l ts mod less than 1. That implies r by l should be far less than 1 by ts, isn't it? What is r by l? R by l is the time constant of the circuit, should be far less than 1 by ts. Sorry, uh, l by r is the time constant of the circuit, right? So let me write it in terms of time itself. So ts by l by r should be less than 1, right? Where ts is the switching time period. So ts should be less than time constant of the circuit. Then only we can approximate it in this way. So that's what we intend as well, right? Then if ts is very comparable to the time constant, then we would get something like this, right? This is not what we expect. We want a very smooth output voltage, right? So what we want is something like this. Sorry, what we want is something like this. So it is the zoomed in version of the e power, it is the zoomed in version of this particular exponential function. So then only we can achieve a smoother DC output voltage. Now let's assume that this condition holds, and try to simplify our existing equations, right? So we'll try to find out the average output voltage from this. Average output voltage, which is equal to, it is simple to think, no, like there is a resistance in which the current is rising and falling based on the input applied, right? So in order to find out the average voltage across this resistance, we can find out the average current. Like we have this current integrated over a switching cycle interval ts gives us average, this is il, gives us the average current. So that average I am representing as il, that is equal to 1 by ts integral kts into 2 k plus 1 ts of il of t dt, which can be approximated as the average of these two, right? If the time constant is far less than the switching time period, then the rise is almost linear, the exponential function will all look almost linear. So it's just the average that we, and we also know that this value is equal to this value, then the average will be the average can be written as, we have denoted it as ilk dash and ilk. So our average il would be equal to il ilk plus ilk dash by 2. So we already know what is il and ilk dash, and we have this approximation that we can substitute and see what we will end up. We have this ilk and we have the expression for ilk dash, right? So let's try to do that. Let's borrow the expression from ilk dash, which we have derived earlier, right? In this mode, yeah, this is our ilk dash. So I would be using this in order to find the average current. So my average inductor current is equal to, if we do go about and substitute our equations as it is, we will end up in this. So that algebra can be verified by yourself. R by L into dts minus e power minus R by L into ts plus e power minus R into 1 minus t into ts by L whole divided by 1 minus e power minus rts by L, right? So let's try to simplify this thing by applying the Taylor series approximation for the e powers. Then we will end up in average IL is equal to Vg by 2R into 1 plus first term 1 minus R by L into 1 minus dts minus 1 minus R by L into ts minus 1 minus R by L into dts divided by 1 minus 1 minus of R by L into ts. So this would result in a very neat equation, that is Vg into duty ratio divided by R. So, and we also know that the output voltage, average output voltage, is equal to average inductor current into resistance. So therefore output voltage is equal to Vg into T. That's how we derive the average voltage for a chopper. Thank you.